This is a nice conceptual example that we are all familiar with. A golf ball with mass 0.05 kilogram, 50 grams, is struck with a club. The force on the ball varies from 0 when contact is made up to some maximum value when the ball is maximally deformed, and then back to 0 when the ball leaves the club, as in the graph of force versus time. This is an actual graphical representation for the force that the club acts with on the golf ball or a baseball or any kind of ball. It's the same kind of force. There's a point of time when the force starts acting. It reaches maximum here with maximum deformation of the ball, and then it goes back to 0 as the ball restores its original shape. Assume that the ball leaves the club face with a velocity of 44 meters per second. Find the magnitude of the impulse due to the collision and estimate the duration of the collision and the average force acting on the ball. We know that impulse equals delta P, the change in momentum. The change in momentum is equal to the final momentum minus the initial momentum. The mass is 0.05 kilogram, and the initial momentum was 0. There was no motion. The final momentum is governed by mass by final velocity. Final velocity is 44 meters per second. So this is the change in momentum, 2.2 kilogram meter per second. This is the change in momentum, which is equal to the impulse. Then, to calculate the period of time, the action time, we use the kinematic formula, delta t equals delta x divided by the average velocity. Since the velocity, the maximum value was 44 and the minimum was 0, so the average would be just half the 44, so it's 22 meters per second. Okay, so here we can calculate delta t, 9.1 by 10 to the minus 4 second. Once you have delta t, you can calculate the force. The average force is delta p divided by delta t by definition. So you have delta p, you have delta t. The answer, it is 2.4 by 10 to the power 3 in newtons. Another nice example that I selected for discussion in this lecture is boxing and brain injury. Boxing was one of the popular sports in the 19th century. At that time, boxers, they were playing with their bare fists, and that can, at that time, usually that can cause injury most of the time. In recent times, boxing became a sport, and there was nice improvement to this kind of sport to minimize the brain injury. So this is the thing that we are going to learn about in this example. The brain, as we know, in our heads, it's immersed in a cushioning fluid. Now, if the head is struck suddenly by a bare fist, the skull accelerates rapidly. The brain will match this acceleration, and there will be large impulsive force exerted by the skull. Now, this large and sudden force, we will now discuss the impulse. The average force multiplied by the action time can cause severe brain injury. But When the boxers use padded gloves will extend the action time. When the action time extended, then the average force will be reduced because the product is the same. The product of the average force by delta T is the same. If delta T increases due to the padded glove structure, then the average force will be reduced, okay? Increasing the time will lead to decreasing the average force, and this will reduce the risk of injury. The same argument can be made for rolling with the punch. So if the head is held steady while being struck, the time interval over which the force is applied is relatively short, and the injury would be great. But if the head is allowed to move in the same direction as the punch, then the time interval is lengthened, and when you lengthen delta T, you are simply reducing the average force. The harm, remember, the injury occurs because of the average force. So reducing the average force will reduce the injury, or reduce the harm. So now we know this nice piece of information. You need always to think not only of the force, but the product of force by the action time. Another example, collisions in automobiles. Usually the manufacturers of automobiles will have all kinds of tests to check on how the seat belt can protect the passenger, etc. They have all kinds of tests to do during the manufacturing process. Usually the energy in the inelastic collision, which is converted into kinetic energy, causes the damage to the vehicle. We have here to apply what we learned about momentum and impulse to real problems so that we understand things better. In a crash test, a car of mass 1500 kilogram collides with a wall and rebounds as in the figure. The initial and final velocities of the car are minus 15 plus going to the left x, the x-axis to the left is negative, to the right is positive as usual. And the final velocity 2.6 meters per second to the right, so it is positive. If the collision lasts for 0.15 seconds, so the action time, the elapsed time through which this force acted is 0.15 seconds. Find the impulse delivered to the car due to the collision and the magnitude and direction of the average force exerted on the car. In order to calculate the impulse, the easiest way is just to calculate the change in momentum. So we need P final minus P initial. So we calculate P initial. It is m multiplied by the initial velocity. M is 1500 kilogram. Initial velocity is minus 15 meters per second. So this is the initial momentum. Final momentum is mv final. This is the mass. This is the final velocity, 2.6 meters per second. So this is the final momentum. So now we are ready to calculate the impulse. P final is a quantity minus P initial, and as I said earlier, momentum is a vector quantity, so direction matters. So minus 2.25 by 10 to the power 4. So now the impulse becomes 2.64 by 10 to the power 4 kilogram meter per second. We know that impulse equals to change in momentum. So now we can calculate the average force change in momentum. We have it from the impulse, this quantity. Divide that by the action time, which is 0.15 seconds, as we are told. So the average force is 1.76 by 10 to the power 5 in Newton. This is 176 kilo Newton. This is a huge force that can cause the injury and the damage. So if there was no seat belt, there was no bags to protect the passenger, the driver, then you are talking about that kind of force which can create all kinds of injuries, including brain damage, bone fracture, trauma to the skin, blood vessels, and the internal organs. In general, a force of 90 kilonewton or greater can break the tibia, can cause its fracture. It can also break all kinds of bone structures, not only the tibia. In general, estimates show that head accelerations of 150 G, G is 9.8 meter per second square, the gravitational acceleration of Earth. So when you deal with acceleration of that magnitude, this can cause injury and harm to the human 50% of the time. So here we are talking about this kind of acceleration acting over a period of 4 milliseconds, or 50 G acting for a period of 60 milliseconds. Okay, this can be fatal 50% of the time. Such great acceleration and great force can cause nerve damage to the spinal cord, where the nerves enter the base of the brain as the head of the driver accelerates during the collision. We have to consider the force and the area. Usually, we assume the area of the chest for the driver, chest and head, 0.7 to 0.9 square meter. So we calculate the pressure equals force per unit area, force per unit area. Okay, and this way we can estimate the impact pressure. The impact pressure, force per unit area, in a typical collision, head-on collision, is 1.9 by 10 to the power 5 in Newton per square meter, which is equivalent to 28 pounds per square inch. Death results in 50% of cases in which the whole body impact pressure reaches 3.4 by 10 to the power 5 in Newton per square meter, or 50 pounds per square inch. To summarize, the threshold for the force that can cause bone fracture is 90 kilonewton. Any force 90 kilonewton or above can break the bones, whether it is the bones of the hand, the leg, the chest, the head, the skull, you name it. And when the acceleration is equal to 150 G for an action time 4 milliseconds, or 50 G for an action time of 60 milliseconds, you are talking about 50% chance of death. When you speak of impact pressure, to take the area of the body into consideration, if the impact pressure exceeds 3.4 by 10 to the power 5 in Newton per square meter, then it's a 50-50 chance to be fatal or not. So I hope you understand collision now better. I selected this problem so that we deal with real numbers. Consider a typical collision involving a 75 kilogram passenger. This is a typical mass for a young adult. This passenger not wearing a seat belt, traveling at 27 meter per second, which is 60 miles per hour, just converted into meter per second, who comes to rest in about 0.01 second after striking an unpadded dashboard during the collision. So now we can do some estimates with these typical values for the mass and the action time and the velocity. So the impulse equals F average delta T. It can be calculated from the change in the momentum, mv final minus mv initial. And from there, we can calculate the average force during the collision. V final is 0. Final momentum is 0. Initial momentum, mass 75 kilogram multiplied by velocity 27 meter per second. And the action time 0.01 second. This is equals to minus 2 by 10 to the power 5 in Newton. We can calculate the acceleration. It is delta V divided by delta T. Delta V is 27. That's the change in the velocity, and delta T is 0.01. So the acceleration is 2700 meter per second squared. Compare that to G, divide by 9.8. So this is 280 Gs. You can tell that this is one of those fatal situations. Of course, if there are airbags and seat belts involved, they will serve to extend the action time, and that way, by extending the action time, this will reduce the force, this will reduce the acceleration, and will save the driver or passengers in such a car. But if there was no airbags and no seat belts, then this is the kind of situation we are talking about. Okay? So here, the effect of having a seat belt or airbags is just to extend the action time. The seat belt or the airbags cannot change the force. They only can change elapsed time. Rather than 0.01 second, it is 0.15 second, for example. This will reduce the force, as you can see here. This will reduce the acceleration. Rather than 280 G, it is 18 G. 18 G, we can do with that. We can live with that. Okay? So now we have a better understanding of the physics of collision.